Hi everyone, this is Ken Miller from the ESNet Science Engagement Team. Filling in for Jason today is on PTO. Wanted to introduce Mariam, and if you want to, Mariam, if you want to introduce your team, we can get started.
Sure. So hi everyone. So I know most of you here. So just a brief update from my side is that I've just moved to Oak Ridge. It's been 3 weeks now, so you might have seen a different change in my title over there. This work is from a project which I'm a co-investigator of, but my team, Imtiaz and George, are the one who've done bulk of the work. So I am going to hand it off to them to present the work which they're doing. So Imtiaz and George, do you want to introduce yourselves and then take it away?
Thank you, Mariam. So I'm Imtiaz Mahmud, and I'm a postdoc under Mariam. I did my PhD from South Korea, Kyungpook National University, and then I moved to LBL as a postdoc, and I have been doing my research mainly relates to the transport layer protocols and also the network layer protocols. George.
Hello, my name is George Papadimitriou, and I'm a PhD student at USC. And currently I'm working on workflows and automating their execution in testbeds like Fabric, Chameleon. And my main research is in data collection and performance analysis on these like distributed infrastructures. So yeah, today we're going to be talking about our work that was done on Fabric about TCP fairness in large science transfers over high throughput links. So, Imtiaz, would you want to start the presentation?
Yeah. Thank you. So hi everyone. Today we are going to present our recent work on studying the TCP fairness in large transfer over high throughput links. And our team, as you can see, that it consists of different scientists from different labs, from RENCI to ORNL, LBL. So I will just try to dive into the main topic. So the motivation behind our work was everything starts with the science flows. Like, as we know that we are dealing with a lot of, we are dealing with science flows, and the science flows has a significantly different amount of data than the traditional networks. Like, we are dealing with large amount of data that is produced in every second. And these data needs to be sent to the cloud for further processing, and then from the cloud to down to the, again, to the nodes. And these data, not only we are doing our research, we are also trying to share our data with different scientific community. So we need to move a lot of data throughout the network. And all of these requires reliability and timely delivery. Some data can be time crucial, like it's time bound, and some data can be time tolerable data, but still we need a reliable transfer protocol, and that can deal with all this big amount of data. And normally in science flows, we are dealing with terabytes of data, not even gigabyte. So these are elephant flows. The network resources are very limited. That's all we know, and the volume of data is very large for the network to handle. So that's why an efficient handling of network resources is the key for successful data delivery, and that's what is our focus. If we see from the abstract view, as a network, from an abstract view of the whole network, we can see that we can understand the network like there is an end-to-end connection, and there is the point-to-point connection. And the end-to-end connection is actually controlled by the TCP constant control algorithm, the data rate. Between the end-to-end connections, like that sender to receiver, it is mainly controlled by the TCP constant control algorithms, whereas there is the AQM algorithms that controls the point-to-point connections, like from each router to other router, how much data can be transferred, which packet should be dropped. So these are controlled by the AQM algorithms. So together, they actually build or control the whole amount or whole data flows, that how a data flow should travel from sender to the receiver. So both of them are very crucial for a successful data delivery and successfully sharing the underlying network. So keeping that in mind, as I mentioned already, sender to receiver ensures the reliable delivery, fair utilization of the underlying resources, and it tries to minimize data. And there is already existing a lot of congestion control algorithms. The different researchers are doing research, and they have proposed several congestion control algorithms, and it gives us another question: which algorithm to choose? For example, when to choose or where to choose, for what purpose, for what data flow, which congestion control algorithms are better. So these types of questions can arise. And also there is different AQM algorithms, and they try to utilize the underlying network, underlying queue differently. They manage the queue differently. They try to provide the quality of service differently. So among them, which one to is better for our network? That's also a challenging issue that we need to address. So keeping all those things in mind, we are actually doing our research to improve the network performance for our data transfer. That's all. That's the main goal. And for that, our target is a reliable data delivery. And we are trying to go through that is current TCP congestion control algorithms and AQM algorithms. We are trying to test them in a robust test bed, and trying to find some innovations, like what is the interplay between the transfer and the queuing routers, we're trying to build a data set for the transfer behavior, like how they are behaving with different changes in the network. And all these things actually is moving us to a new innovation of better network with better congestion control algorithms. That congestion control algorithm may be from the existing ones, or maybe something new with the advancement of AI technology. So that's the main objective of our work. Just before starting or dive into our experimental or the discussion session, I would like to give a brief overview of the existing of the algorithms that we are dealing with. Firstly, for the transport layer protocols, the TCP congestion algorithms, we are dealing with BBR version 1, BBR version 2, Hamilton, Cubic, and Reno. So just a brief overview for BBR version, as we all know, it was developed by Google recently, like in 2016. It aims to maximize the network throughput by estimating the available bandwidth and delay of the network path. So actually, the key difference from the traditional congestion control algorithms to the BBR is that it is actually a model-based approach. Here, it tries to adaptively adjust the sending rate based on the estimation of the underlying network. It tries to estimate how the estimator model the underlying network, and based on its own modeling, it tries to adjust its sending rate. So that's the key idea behind BBR version 2, BBR version 1. BBR version 2 also employs the same idea, but it actually improves BBR version 1 further. It incorporates several improvements to better handle network congestion and improve fairness. And most importantly, it includes the more accurate congestion signaling and responsing mechanism. It incorporates that, because in the previous BBR version 1, it actually it was not responding to the network congestion signals. So BBR version 2 tries to address that, and it implements a better congestion signaling response mechanism, and by that it also tries to improve the overall performance, especially for the high latency links. And for the Hamilton TCP, it is mainly designed for the data center network, where we have a very high bandwidth and low latency link. It focuses for obtaining high throughput and low latency in large scale data center environments, and it utilizes a combination of ECN, that is explicit congestion notification, as a feedback mechanism, and also explicit congestion control, like the packet losses and the delay, and it tries to adjust its sending rate based on those feedbacks from the network. And in the case of Cubic, as we know, Cubic and Reno both are the mainly loss-based congestion control algorithms. When there is a loss, they reduce the sending rate, whereas whereas Reno actually, when there is a loss, it reduces sending rate to half. Then it tries to increase the sending rate gradually, one by one packet by one packet, in that way, linearly. In the case of Cubic, it actually for the improvement, it applies the cubic function rather than the linear function, and thus it actually obtains a much better throughput normally than the Reno, and that's the key reason that the Cubic is the most widely used congestion control algorithms throughout the entire network. And for a small background on the QM algorithms, like we are actually in these experiments, we employed FIFO, RAID, and FQ codel for the QM algorithms. Just for the basic idea, FIFO, as we all know, that is the first in, first out, that simply takes all the packets in the queue. Then whenever the queue is full, it tries to drop the packet from the tail. So that's the key, main mechanism here. And as a point-to-point flow control algorithm, FIFO does not provide any congestion control mechanism and may lead to buffer bloat and increased latency under heavy network congestion. Actually, when the network becomes fully congested, then it starts dropping the packets, and then this drop actually goes as a signal to the congestion control algorithms that, well, there is a network congestion. So the congestion control algorithms are getting the idea that the network is already congested at the very end when the network is actually congested. So that's a thing, that's the view from the FIFO, that it actually drops the packet at the very end when the queue is totally full. In the case of RAID, it actually it is better designed to prevent congestion, collapse, and improve fairness. So it actually, rather than waiting for the queue to become totally full, it drops the packet randomly whenever it sees that there is a probability that the queue will be becoming full. So before the queue actually becomes full, it starts dropping the packet randomly. This random drop of packet signals to the end-to-end congestion control algorithms like to reduce the flow of data, and thus helps to maintain a stable network performance. So it is a bit more aggressive than the FIFO, that it actually tries to reduce the congestions before the congestion actually happens. It tries to randomly discard some packets before the congestion window, the queue actually becomes full, and that sends that signal to the congestion control algorithm. That helps the congestion control algorithm to reduce the flow of data so that it can avoid actual congestion. So that's the RAID approach. There is also the FQ codel. It is one of the most advanced AQM algorithm that actually combines the queuing, fair queuing, and the codel algorithm. So it assigns separate queues to different flows and manages the queue lengths based on per flow pacing. So FQ codel aims to obtain low latency, low packet loss, and fair bandwidth allocation among different flows, particularly in network with diverse network traffic patterns. So basically what is happening here, that is FQ codel divides the existing queue in several queues, and for each flow going through the router, it allocates a separate queue for that router, that flow. So, and then it also combines the codel technique. So it does not wait for the queue to become totally full. It actually predicts the condition, and then it tries to drop the packet and signal back to the congestion control algorithm. So that's how it, in one hand, it tries to signal the congestion control algorithm like there is a possibility of congestion, and at the other hand, maintaining different queues for a separate queue for each of the flows. It tries to maintain or give the better fairness for each of the flows. So it tries to deal with the flows much better fairly. So there's the key differences inside among the three AQM algorithms. Then I would like to just give a brief overview of the bandwidth delay product, which actually gives what can I say, that the leads the network, dominates the network, and controls the network flows in several ways. For example, just if we try to understand the key idea behind that, we know that the bandwidth of a network, bandwidth of each pipe that we are using, it is fixed. The fixed bandwidth, here we are saying that that is the bandwidth, for example, it is a data rate and it is round trip time. So the bandwidth of all the a packet, a tunnel or a pipe is fixed. So if we want to obtain that bandwidth, and if we can send the packet with the minimum RTT, like when the round trip time is the minimum. So if the round trip time is here and the bandwidth, we are utilizing the whole bandwidth, that means we are actually utilizing the network to its full capacity. So the idea is that when the RTT is low, that is we are actually obtaining, we can send the packet with the minimum delay. And when the delivery rate is the high, that is we are utilizing the entire bandwidth of the network. That means we are actually utilizing the network in full. Now, in reality, it is very hard to obtain. For example, in the case of Cubic, Cubic waits until it gets a condition notification, like until when the packet there is a packet drop. The packet drop signal that, well, there is a condition, then it stands off. Then it reduces its sending rate. So that's what is happening. That's how Cubic is actually operating here in this point. And this graph, this space is given for the queue length. So when there is the queue length, the queue length actually gives an extra boundary for the network to store some packets in the network. So in the queue, the packets are stored, and they are actually, as the packets are stored in the queue, they are giving some queuing delay. So that delay actually increases the RTT, and that's how after certain the queue is limited. So after certain point, we can go we can reach to the highest RTT level. So after that point, the packets are dropped. So that means then we are not getting an RTT for that packet. So this is the highest RTT level, and in that at that level, actually Cubic works. That when the RTT is high, that means the queue is full. Then it actually drops the packet. The queuing algorithm drops the packet, and after that it reduces the sending rate, and then it again tries to fill up the entire queue, and again it goes this point. So this is we're saying that this is the operating point of the Cubic. So although we are we are utilizing the bandwidth in full, but we are actually also trying to utilize the queuing discipline, the queue fully. So that's the key point behind the Cubic or Reno, that is the loss-based constraint control algorithms. To alter that, BBR comes. BBR says that, well, if we can reduce the sending rate, that we can reduce the RTT, that means we are better utilizing the network. And that's why Cubic is trying to minimize the RTT. So it is not focusing to fully utilize or fully to utilize the full capacity of the queue. Rather, it tries to utilize only a small portion of the queue, so that it can keep the queue, it can utilize the whole network. And for that, actually, there was some previous theory, like we need the 1 BTP in-flight, 2 BTP in-flight data. So 2 BTP means that this is the bandwidth delay product. So 1 BTP for going and 1 BTP for coming. So 1 BTP means that when we are sending a packet, so 1 BTP packets are going, and then for that RTT to come back, another BTP packets are going. So total 2 BTP packets are set by the constraint window for sending at a time. So that's how that's what the BBR actually implements. And so BBR tries to offer the gist of the idea is that BBR tries to reduce RTT while it tries to keep the keep the bandwidth utilization to the full. However, this case is only true for BBR in the case of large buffer, where in the case of a small buffer, BBR operating point actually exceeds the point of the Cubic. So Cubic actually, when this is again for the condition control for the AQM algorithms, like the queuing algorithms, so that is the highest level of queuing delay. So after that, the Cubic starts to drop the packets, but in the BBR, there is no mechanism to drop a packet. Rather, it doesn't care about the condition signals. So it tries to push more and more packets into the network. And that's how BBR, in the case of low buffer, a small buffer, it actually exceeds the optimal operating point, and it goes beyond the operating point of cubic, and thus it causes a lot of significant amount of retransmissions. So that's the problem in the case of BBR for a small buffer, but in the case of large buffer, BBR can obtain a better throughput for the round trip time. But in reality, if we see the curve here, the good curve for the BBR and the cubic, although theoretically it should operate or it should obtain better, but in reality, with the increase in the BTP, that is the buffer sizes, that is with the introduction of the deep buffer, whatever we say, when the buffer increases, the BBR performance drops, whereas cubic performance keeps increasing. The thing, what happens, like in the low buffer cases, as we are seeing here, the BBR does not care about the losses, so it keeps sending at the same rate. That gives it an upper hand over the cubic. Whereas in the low buffer cases, when it is actually operating with cubic, so it operates at the lower, it tries to keep the, it tries to not utilize the whole queue. Whereas cubic is there, it tries to utilize the entire queue. So it actually gets an upper hand over BBR because it is actually pushing more packets in the queue. So there is more packets, means more packets that more throughput cube is getting than the BBR. So that's how with the increase in the buffer, the cubic is getting upper hand over BBR. So that's the main why I'm spending so much time here, because this is the key idea that actually affects the future, the existing behavior of the different AQM algorithms. That's why we need to understand that this idea. So anyway, so now we will go to the experimental section with George, and then I will try to explain the what results we have obtained from our experiments.
Thank you, Imtiaz. Can you control the slides for me?
Yeah, I can. I can control.
Yeah. All right. So we chose Fabric to do to conduct our experiments, and a few things about Fabric is a pretty brand new testbed, and I think it's almost ready to go to its production phase. So Fabric is a nationwide instrument that's supported by NSF, and it was built to support large-scale experiments. It has multiple sites across the US and also across borders nowadays. And it offers like programmability in all of the sites, meaning there are compute and there's compute and storage resources there, and also accelerators such as GPUs and FPGAs that are interconnected with high-speed dedicated optical links between these sites. And additionally, it offers a user-friendly API that you can interact with the testbed and also create your experiments there and control them. Next slide, please. So for our experiments, we created a dumbbell topology with 2 nodes in Clemson, 1 routing node in Washington, another routing node in NCSA, and 2 nodes at TAC. And the total round trip time for this deployment was 62 milliseconds. Imtiaz, can you click one more slide? Thank you. So for creating the topology, we used the FabLib API. And we acquired dedicated NICs on each of the nodes. And for the clients and the receivers, we used ConnectX-5 cards that have dedicated ports of 25 Gbps. And for our routers, we used ConnectX-6 cards. And that was mainly done because we wanted for the bottleneck link between the 2 routers to be over the bandwidth that we were going to test for. So with this topology, we have created a single bottleneck bandwidth between router 1 and router 2. And that's where we were applying all the AQM logic and the limitations in terms of like speed in a network. Additionally, we assigned there were /30 across the entire deployment. And we enabled jumbo packets of MTU that was 8,900 bytes. And to make sure that we had connectivity across clients and servers, we applied also static routes on all of the nodes. So our experiment is fully reproducible thanks to like the Fabric and the Fablib API. And we are sharing like our entire Jupyter notebook that deploys this experiment and also controls all of the configurations and executions that we did to collect data. And you can find that on GitHub, and we will have also like the main repository link at the end. Next slide. So based on the background that Imtiaz already presented, for the experimentation here that we did, we tested about 810 scenarios. And as you can see, we had some heterogeneous configurations, such as BBR-v1, BBR-v2, HTTP, and Reno versus Cubic. And also the homogeneous version of these, and that was across like the entire spectrum of these like 5 CCA algorithms. So the way we did this was that we assigned 1 CCA on each of the senders. And the receiving side, or like the server side, did not participate in that part. Like the CCA was assigned on the clients only. And we tested for FIFO, FQCodel, and RED on the link between router 1 and router 2. And we also applied different queue lengths or buffer sizes on router 1. And the queue lengths were dictated all the time by the BTP number. So across our experiments based on the bottleneck bandwidth that we were applying, the BTP was also changing. So that number was also getting affected. Now, apart from that, as we were scaling the bottleneck bandwidth, we were also scaling the IPERF3 configurations that we had, because that's what we used to acquire measurements during our experiments. So in order to avoid any limitations in terms of like CPU usage from IPERF3, because it's single-threaded, sorry, it's single process. I'm not sure if it's single-threaded or multi-threaded. I think it's single-threaded, and that's why we did that too. We scaled the number of processes that we had, and also the parallel streams that we were sending over. So for example, for 100 Mbps, we used 1 flow per client. And then for example, for 25 Gbps that we tested, we did 500 flows total, 250 per client, but we did 25 IPERF processes per node with 10 parallel streams. Next slide. So on the right side here, you can see like our Jupyter hub cell with the configuration. And on the left side, we have a pseudocode for our experiments. So the way we did it was that for its AQM type and for its CCA configuration and for its speed configuration that we had, we were calculating first the BTP based on the formula you see on the right-hand side. And the way we did it was we got the bottleneck bandwidth that we had. For example, let's say 100 Mbps. We multiplied by the RTT, that was 62 milliseconds for our deployment. And then in order to get that in bytes, we divided by 8, because we had our speed configuration in bits. So after we acquired the BTP number, we calculated the buffer sizes that we wanted. And for its buffer size, we applied the AQM settings and the buffer size on router 1. And for example, you can see on the bottom of the slide, we used TC and the Q disks to do that. And this is the example from the FQ Codel application. And after we've done that, we repeated our experiments for 5 times to collect to collect an average number of the measurements. And for 1 through the number of processes we wanted to spawn of iPerf, we were starting the servers, we were starting the clients, and we were continued the experiment for 200 seconds every time. And then we waited for 210 seconds, and then we were killing the servers, collecting the data, and we were doing that all over again. And on the second to the bottom pane, you can see how we did the iPerf3 commands. The server command is very simple, but for the client command that we used, that's where we were applying the CCA algorithm and also the number of flows, and we were fixing the MTU size to 8900 for the experiments. And now Imtiaz will go on and present results and discuss a little bit about our findings.
Thank you, George. So now just for the observations that we are getting from the from our experiments. So first I will try to go through for the observations when the AQM is fixed, like the AQM is FIFO in this case, in this slide. So when the AQM is fixed like FIFO, then we can see that with the increase in the BDP, we can see that the throughput changes a lot. And the both the important thing that we should remember, like in this case of FIFO, the entire bandwidth, that is, for example, here 100 Mbps, here it was the 1 Gbps, here it was 25 Gbps. So all the entire bandwidth could be utilized when FIFO was the constraint control. FIFO was the AQM algorithm. So that is a key point to observe. Then with the we can see that there is a bandwidth dependency and there is an equilibrium point, that when for example cubic, this is the inter-congestion control algorithm experiments where BBR one center is sending through the BBR and the other center is sending through cubic, and we can see there is equilibrium point, for example, for the 100 Mbps link at around 2 BDP. And this equilibrium means that in this point, both the BBR and cubic could share their bandwidth, share the network equally. And it was also reported by the previous previous works, like 2 BTP is the optimal operating point for BBR. We can also see that this operating point is actually not fixed, rather it shifts with the increase in the bandwidth. So for example, here the bandwidth is 100 Mbps, here the 500 Mbps, so it moves to right around 3 BDP, and it keeps moving right, so around 2.5, 3 or 4 BDP with the increase in the bandwidth. So that's one observation, and the reason behind this aggressive behavior of BBR, especially when the BDP is low and the BDP is high. So it first thing is that the BBR does not respond to any conditions, any condition notification. So at the very beginning, it occupies the entire bandwidth depending on the BTPs, and at the later part, because there is a significant amount of buffer size available. So in this case, the BBR is bound by its 2 BTP cap. So actually, as I previously mentioned, that as 2 BTP is optimal for the entire network, that BBR tries to keep the sending rate. So for the 2 BTP sending rate, it before the 2 BTP, when the buffer size is less than 2 BTP, BBR gets upper hand, and when the buffer size is more than 2 BTP, it gets the lower, BBR gets lower hand. And the reason is that it is limited by the BDP, that it cannot overthrow the network with beyond 2 BTP. And in the case of lower cases, in the lower part, it does not respond to the packet losses, and BBR has a very aggressive startup phase. Both contribute to its higher getting upper hand over the cubic. Whereas in the case of higher BDPs, where BBR keeps sending at the same rate, where Cubic can increase its sending rate because it can occupy the entire bandwidth, entire queue size. So that helps Cubic to get an upper hand over over BBR with the increase in the BDPs. And this equilibrium point actually shifts, and we believe that it so the equilibrium point can be corresponding to the bandwidth, available bandwidth, and the network, the RTT and the network resources. So it has some dependence on those also. Apart from the only bandwidth and the BDP, there can be some other affecting factors that is affecting them to shift to the right. And in the case of BBR version 2, as we know, BBR version 2 implements some mechanism to respond to packet losses. So that's what is happening. So I will go through these two later. Rather, I will focus on from the 1 Gbps link here. So we can see that still we can see a equilibrium point. For example, here the equilibrium point lies between 1.5 BDP. In this case, it lies within 4.5 BDP, around 5 BDP, and here it lies around 6 to 7 BDP. So again, the equilibrium point shifts, and the reason why the BBR version 2 is losing its power, because BBR version 2 after certain, it also keeps maintains a 2 BDP cap, and it cannot increase beyond that rate, but Cubic can increase, so Cubic is getting an upper hand. There is also another factor, that is BBR version 2 is actually responding to packet losses. So when it is responding to packet loss, when the Cubic is actually occupying the entire queue, it is causing packet losses, and that packet losses are also causing BBR version 2 to reduce its sending rate. So that's why BBR version 2 actually performs worse in the case of high bandwidths than the BBR version 1. And we can see the equilibrium point was previously fixed for the low BDP around 2 BDP or 2.5 BDP. But in this case, BBR, the equilibrium point moves left. It is less than 2 BDP. And what we believe that for the 500 Mbps and 100 Mbps, there is also an equilibrium point, but that may be within 0.1 or 0.2 BDP cases. And it was actually reported by some other researchers previously that there is also an equilibrium point, but it is at the very lower end. So what is happening that as BBR actually responds to the packet loss BBR version 2, so it loses its fair share and Cubic gets an upper hand. Now, so why BBR is getting an upper hand at the very beginning? At the very beginning, BBR is getting an upper hand over Cubic because BBR has a starting flow, that the startup phase of the BBR is rapid, considering to the Cubic. So because of the rapid starting flow, startup behavior of the BBR gets an upper hand at the beginning, but with the flow of passage of time, BBR, there is two things that is going against BBR. One is the sending rate, its sending rate is fixed, and the second thing is that it is in the case of BBR 2, it is also responding to packet losses. So that forces BBR version 2 to actually lose its fair share with the increase in BTP, that is increase in the bandwidth, bottleneck bandwidth, bottleneck queue sizes. So that's the two observations that we can understand from here. And if we see to the Hamilton, so in the case, Hamilton is almost always getting an upper hand over Cubic, especially for the small bandwidth sizes. With the increase in even with the increase in bandwidth, that is with the increase in bandwidth, the pipe bandwidth, we can still see that the Hamilton is getting an upper hand, but that upper hand gets a bit lower. So what is happening here? The in the case of Hamilton, it actually operates based on the estimation. So it estimates that depending on the delay and the packet losses, that what will be its sending rate. So when the bandwidth increases, so with the increase in bandwidth, the queue or length also increases. And this introduces an extra delay because there is a lot of queue, so it can store more data. Storing more data introduces a more a long elongated RTT. That causes Hamilton to think like, well, I may be facing some congestion in near future. So that's why it reduces its sending rate, and that's why it is showing a downward curve with the increase in the BDP. So that is the reason for the behavior of Hamilton here. And in the case of Reno and Cubic, we can see like the with the increase in BDP, Cubic is always getting an upper hand over Reno, and that's very obvious. Like whenever there is a packet loss, Reno tries to increase its sending rate after decreasing. First it decreases, then it tries to increase the sending rate step by step, that linearly. Whereas Cubic utilizes the cubic function, and that gets an upper hand over Reno for utilizing or getting and better throughput for the higher BDP scenarios. So that's what is happening for the here. Then we will go to the FQ codal algorithm. So here, the key observation that I would like to show that here we are not, we could not utilize the entire bandwidth. So especially for a case of throughput 25 gigs, we can see that we are obtaining like 2.1 gigs. So although for the higher bandwidth scenarios, FQ codal could not utilize the entire bandwidth. So that was a key observation from us for the AQM algorithms perspective, and for the constraint control algorithms perspective, because FQ codal provides a separate queue for each of the flows, and that makes the flows much fair to each other. And that's what is happening, that BBR is always fair, now is much fair to the cubic, and there is no equilibrium point that we can see here. Interestingly, BBR is always getting an upper hand, and it is pretty obvious because BBR can operate with disregarding the condition notification, so it can keep the sending rate to the it can maintain a sending rate constantly. That gives it an upper hand of a cubic, whereas cubic actually responds to the packet losses, so it has a lower sending rate or lower throughput than the BBR. In the case of BBR version 2, it actually performs a bit lower than the BBR version 1 because it responds to the packet losses, but still it maintains a 2 BDP sending rate. And it responds to packet losses when the packet loss is less than 2%. When the packet loss is greater than 2%. So when the packet loss is less than 2%, it does not respond to the packet losses. So that gives it an upper hand over cubic also. So that's why BBR is performing, both BBR version 1 and BBR version 2 is performing much better than the cubic, a bit better than the cubic. But the most significant thing is that with FQ codal, both of them are very fair with cubic or any other constraint control algorithms. And when we see for the Hamilton, actually here Hamilton also has the loss based, or it responds to the packet losses. So Hamilton and cubic are performing almost in a similar way. And in the case of cubic and Reno, again cubic is getting an upper hand because cubic is using the cubic function to increase the sending rate rather than the linear increase. So that is why cubic is getting an upper hand over Reno. And when the AQM algorithm is read, so interestingly with read, we can see a quite imbalance in the network utilization. For example, firstly, RAID fails to utilize the entire bandwidth, especially for the 25 gigs when there's the high bandwidth scenarios. Like we can see, it is only utilizing 1.3 gigs, although there is a 25 gigs of bandwidth available. And for the Reno and Cubic, and for the BBR version 2 and BBR version 1, it is utilizing around 2 gigs, where 2.5 is available. And we can see a quite imbalance, like the BBR is getting BBR is actually choking up almost all the bandwidth, whereas Cubic is getting nothing. So it's almost near, the throughput is near 1 Mbps or near 0, whereas the Cubic is getting a throughput of around 2 Gbps. And this is actually true for all the bandwidth scenarios. So the reason behind this is actually rate utilizes the drop probability. So based on the probability that, well, I can, when it says that, well, there can be a congestion, it starts dropping the packet randomly. And this random dropping of the packet actually signals Cubic to reduce the sending rate. However, the BBR does not respond to such congestion, such response. Rather, BBR keeps going at the same rate. And this drop probability of rate is mainly dependent on the arrival rate. So rate counts on the arrival rate for determining its drop probability. And as when it says that, well, arrival rate is not reducing, so it keeps dropping more and more packet, and that forces Cubic to limit its sending rate much lower, further, and it gives the BBR version 1 an upper hand over that. So that is happening here. And in the case of BBR version 2, it is also getting an upper hand over the Cubic, definitely a significant upper hand, but a bit lower than the BBR version 1. And the reason behind that is BBR version 2, or it actually responds to the packet losses. But as I mentioned before, BBR version 2 does not respond to the packet losses until the packet loss is more than 2%. So when the packet loss is less than 2%, in that case, BBR version 2 is also not responding to the packet losses. So it is not reducing its sending rate. That actually forces the rate to drop more and more packets, then causes the Cubic to reduce its sending rate. So that's why Cubic is always getting performing much lower, much worse than the BBR version 1 or BBR version 2 in the case of when the AQM algorithm is the rate. And when we see for the a Hamilton TCP, so in this case, Hamilton is performing, it is also getting an upper hand over the Cubic, but much lower than the BBR version 1 or BBR version 2. And the thing is that actually Hamilton responds to the packet losses, and it also actually introduces a probabilistic approach. So the interaction between the two probabilistic approach actually is the key reason behind this behavior. Although rate signals Hamilton, but Hamilton sometimes Hamilton only reduces when there is the increase in delay and the packet loss both. So that's why the reducing rate is much lower than the Cubic. So as the reduction is lower than the Cubic, so it gives an upper hand over Cubic in the case of rate. And in the case of Reno and Cubic, they both respond to the packet losses, and that's why they are always showing almost the same behavior. Same share of data, so they are fair. But unfortunately, we can see with in the case of BBR version 1 or BBR version 2, they were at least utilizing 1.3 gigs of total bandwidth for the 25 gigs. But in the case of 25 gigs for the Reno, it is only utilizing 9.5 gigs, and for the Hamilton also 9.5 gigs. And it's true for almost whenever the bandwidth crosses 1 Gbps. So their its capacity to utilize the entire bandwidth, it actually reduces. So overall, if we see in this graph, we are trying to show the overall link utilization. And if we see that in the case of FIFO, we are always getting almost full bandwidth utilization. In the case of FQ Codel, the bandwidth utilization is a bit lower. In the case of the 25 Gbps so bandwidth, it is utilizing almost 80% of the bandwidth. Whereas in the case of RED rate, so the bandwidth utilization significantly reduces after 1 Gbps. So it reduces right around 60 to 65 for 10 Gbps and around 40% for the 25 gigs. So it is a significant reduction. So we can during our experiments, what we have experienced that like the bandwidth utilization mainly depends on the AQM algorithms that we are choosing. So depending on the AQM algorithms actually dictates that how much will it be possible for us to obtain to utilize the entire bandwidth or not. Whereas the congestion control algorithms, whatever bandwidth we give, so they are normally capable of utilizing the entire bandwidth. So that's the two things that we have observed in our experiments. Apart from that, for the Jaynes fairness index, as we can see, as we have already experienced, I have already explained in our previous slides that the reason behind the unfair behavior. So FQ Codel again ensures the highest fairness, even in the case of Jaynes fairness index. The FIFO is the next, but in the case of RED, there is a significant gap between the bandwidth between the fairness that I have already explained. So I will not try to explain that again because I have already explained those. And in the case of intra congestion control algorithms, so in this case, when only BBR or only BBR version 2, Reno or TCP Cubic is working, there is no other flows in the network. In that case, they could utilize fairly the available bandwidth. So that is, we are observing irrespective of the AQM algorithms, they could utilize bandwidth fairly in the case of intra congestion control algorithm experiments. So in a conclusion, there is some game theory in play with the changes in the BDP that we have already observed. The choice of queuing algorithm plays a significant role in obtaining high fairness for flows. Although Google's BBR version 2 transfer protocol shows better performance in terms of retransmission than Hamilton, but lacks fairness when competing with cubic flows. And we should keep in mind that we are using a cubic and a Hamilton for the DOE. So in the other hand, FQ Codel shows superior fairness. However, it fails to utilize the full capacity, especially for the 25 gigs. And what we believe that it mainly corresponds to some internal parameters of the FQ Codel. So further research on fixing those internal parameters can actually improve FQ Codel's performance even for the 25 gigs or beyond. So in conclusion, we can safely like combining FQ Codel queuing algorithm method with BBR version 2 may offer a best balance of low retransmission, high fairness, and good bandwidth utilization across a range of scenarios. However, as you have already observed, the performance can vary scenario to scenarios, but and overall we can choose among these two combinations like BBR version 2 and FQ Codel to give an overall better performance in terms of retransmission, fairness, and bandwidth utilization. So that's all for today's presentation. And as a future work, we are also conducting some additional, actually in these experiments, we have already observed their pattern of behavior. Now we are trying to understand what is causing this behavior in more deeper. So we are trying to gather all the data in a timely manner. So we are conducting more experiments to gather further insights into the buffer users. What is the buffer at each time stamp, at each time, how the buffer is changing? That is, we are trying to observe. Then we are trying to monitor the internal parameters like RTT, congestion control, congestion window, and the retransmissions as the end users for each and every packet. So we are also trying to grab those data, and then we are trying to create a whole data set that will give us a complete overview that with the changes in the congestion window, what happened to the queue, and with the changes in the queue, with the changes that the queue made, like the packet dropped. So what changes was caused in the congestion control algorithms here? So the interplay between these two will be fully observable, and this will also create a much better, a bigger data set for the ML-based congestion control algorithms for future training. So we also have a plan for to design and develop an ML-based congestion control algorithm for future internet based on our observation, based on the data set. So, and to fine tune the constraint code algorithms. So, and in the next, we have just a quick reminder that we have an upcoming in this workshop in the SC 2023, and the paper submission deadline is August 11th. And the notification of acceptance will be September 8th, and the workshop date is on November 12th. So everyone is encouraged if you have to submit your paper in this workshop. So that's all for today's presentation from our side. If anyone have any questions.
Good, thank you very much. That's very nice, a lot of information. Very interesting results. Does anyone have any other questions? Any other feedback or challenges? All right, I think Miriam shared the emails there, so if anyone does have any future questions or anything else, the emails are in the chat. So yeah, I want to thank you for presenting and going through all the research and details. So feel free to reach out if they have any questions there, and I guess that'll be everything for today. Thank you all very much, and thanks again for presenting.
Thank you very much.
Yep, have a nice day.
Yeah, have a nice day.